wait. Please make sure this is okay. Okay, so an alkene is basically a double bond between two carbons here. And do you guys remember what is the hybridization of this carbon right here that is double bonded? sp2 hybridized, that's right. And if it's sp2 hybridized, it is going to be flat and planar. And this double bond right here has no free rotation. It's locked into that position, right? So let's go over the definition of a sigma bond and a pi bond. So a sigma bond is a direct overlap between two orbitals that could be unhybridized or hybridized. So unhybridized orbitals could be unhybridized s orbitals or unhybridized p orbitals. So the things that are unhybridized s are hydrogen atoms. The things that are unhybridized p orbitals are halogens, like the chlorine, bromine, iodine, fluorine. Hybridized orbitals are like sp3, sp2, or sp. Right. These bonds are stronger than the pi bonds because they are held more tightly together. Like the electrons are closer to the nucleus. Pi bonds are side by side overlap between two p orbitals. So there's a parallel overlap between these two p orbitals here. Right. These electrons are further away from the nucleus, which is held more loosely. So this is why the pi bond is weaker than the sigma bond. So we know that hybridization is between these four orbitals, 1s and 3p over here. If an atom is sp3 hybridized, that means that all of these orbitals are combined together, meaning that that sp3 atom will have four sp3 hybrid orbitals and 0 p orbitals, because we are combining all of these four orbitals together to make this hybridized sp3 orbital. All those four are gonna make four sp3 orbitals here, right? Yeah. So if an atom is sp2, then we are going to combine these three orbitals, 1s and 2p orbitals. That gives us 3 sp2 orbitals and 1 remaining unhybridized p orbital. If an atom is sp hybridized, then we would have 2 sp orbitals and 2 remaining p unhybridized orbitals, right? And this is important because let's say we look at these sp3 carbons here, right? And we know that these H's are unhybridized s. Let's draw them out, but in their orbitals to show the sigma and pi sigma bonds, no pi bonds, right? So we know that this carbon is sp3, meaning that it has 4 sp3 orbitals. Let's draw those 4 in right now, where sp3 orbitals look something like this, where there's like a small lobe here and a bigger lobe there. A p orbital looks more like a dumbbell shape, where they're like equal in size, like that, right? sp2 is similar shape as sp3 and sp as well. Okay, so now we see that this carbon is sp3 and there's 4 of them, so let's draw them those 4 right now. That's 1. This is another one. That's the 3rd one, and this is the 4th one. The s orbitals are spheres, so the hydrogens have s orbitals, so they are all spheres like that. Okay, let's draw the same thing for the other carbon. Those 4 sp3 orbitals like this. 1, 2, 3, and 4. And those 4 unhybridized s orbitals like that. These direct end-to-end overlap between the orbitals are the sigma bonds. But not all of these sigma bonds are the same, because this sigma bond right here is between an s orbital on the H and the sp3 orbital on the carbon, right? But the sigma bond here is between the sp3 carbon and another sp3 carbon. Like this end-to-end overlap here is overlapping between an sp3 orbital and another sp3 orbital. But this overlap here is between an sp3 orbital and an s orbital. So not all of these sigma bonds are the same, but they are all sigma bonds. And we see that this sigma bond can do free rotation because we are able to rotate these bonds because they will still overlap with each other. Like nothing's gonna break that bond if we rotate it. Okay. Now let's move on to the sp2 alkene and see what that looks like in orbitals. So since these carbons are sp2, they have 3 sp2 orbitals. One of them is that, the second one is that, and the third one is that. Right? The hydrogens are still s spheres. And let's do the other one now. That's 1, 2, and 3. Okay. Hydrogens are still spheres. But now we see that since this is an sp2 carbon, we also have an unhybridized p orbital, where that unhybridized p orbital is going to look like this. Right? Where the sigma bonds are the direct overlap between these orbitals. And the pi bond is the parallel interaction between these two p orbitals here, right? This is why double bonds cannot freely rotate, because if you try rotating this would no longer be parallel. Like if you rotated it, the p orbital would turn and not be able to bond with that p orbital anymore, right? That's why double bonds are not freely rotated, because you would break this pi bond. So this is a pi bond between two p orbitals, which cannot be rotated unless you are above 300 degrees Celsius, but that is rare. Okay. And the purple ones are the sigma bonds. Okay. And then this is 2 chapters ahead, like the alkyne chapter, but this relates to the thing we just did, because these are now sp hybridized, where there's 2 sp orbitals on that carbon. And 2 p orbitals here, 1 and 2. So the sigma bonds are here. And then the pi bonds are between the 2 parallel p orbitals. So like that. Where the triple bond is the strongest bond because it has a sigma bond between these 2 carbons and 2 pi bonds. Right? One pi bond is between these 2 p orbitals, the other pi bond is between those 2 p orbitals there. Pi bond there, pi bond here. Okay. And also another thing is that the stronger the bond is between 2 atoms, the shorter it is, because the electrons are closer to the nucleus. Okay. Okay. So now let's go over the position terms for this chapter. When you have an alkene, the carbon directly on the alkene is called the vinylic position. The carbon adjacent to that alkene, or 1 carbon away, or alpha to that alkene, is the allylic carbon. 1 carbon away, the benzylic carbon. And this is more for the alkyne chapter, but 1 carbon away from the alkyne is the propargylic carbon. Right. So for this chapter, it's going to be vinylic, allylic, and benzylic. Okay. Now let's go over the acidity of alkyne, alkene, and alkane. So which one of these has the highest S character? SP, SP2, or SP3? SP, that's right, because SP has 1 out of 2 S character, which is 50% S. SP2 has 1 out of 3 S character, which is 33% S. And SP3 has 1 out of 4 S character, which is 25% S. So S character increases from right to left, or SP has the highest S character, SP3 has the lowest S character. The more S character an atom has, the closer it is to the nucleus. Closer electrons are to the nucleus. Okay, so let's look at these acids here, the acids on the alkyne, alkene, and alkane. And let's say they get deprotonated into these conjugate bases here. Which one of these conjugate bases do you think is the most stable? The one that is going to be closest to the positive charges. Right, because we know the nucleus is full of protons, which are positively charged. So which one of these negative charges is the most stable based on that? So the one that has the most S character, SP, is going to be the most stable negative charge, because this negative charge right here is on the SP atom, which has the most amount of S character, which means that this negative charge is closest to the nucleus. And if it's closest to the nucleus, it's stabilized because the nucleus has positive charges and opposite charges attract. Negative charges attract positive charges. So that's why the SP alkyne is the most acidic. Right. So the stability of the conjugate base increases from right to left, where the most stable conjugate base is this alkyne anion here, which makes this a weak or strong conjugate base if it's stable. Is it going to be, yeah, weak? Yeah, that's because if it's very stable, it's unreactive. And if it's unreactive, it's weak. Weak conjugate base means strong acid. So the strongest acid here is the alkyne, where the pKa of the alkyne is 25, pKa of the alkene is 44, and pKa of alkane is 50. The lower the pKa something has, the more acidic it's going to be. Okay. Yeah. Yeah. So for the conjugate base, this here, we're looking at these hydrogens here, where this hydrogen is on an sp3 carbon, this hydrogen is on an sp2 carbon, and this hydrogen is on an sp carbon. When, let's say, a strong base comes in, like NaNH2 or NH2 minus, it comes in and grabs the hydrogen and makes a negative charge on that carbon right there. Right. Oh, let me show that. What that means. So let's say, for example, we have a strong base like N-butyl lithium, which is strong enough to grab that proton. 1, 2, 3, 4. Actually, 1, 2, 3, 4. Yeah, this is a strong base right here. It's going to grab that hydrogen. The bond between the carbon and hydrogen is gonna move and give that carbon a lone pair of electrons, which gives that a negative. So this is the conjugate base of that acid right there. This is the conjugate base of this acid, because let's say that base comes in and grabs the hydrogen, it's going to form this conjugate base right here. This is the conjugate base of that alkyne, because that's the negative charge that's formed when this gets deprotonated. In 118A, we figured out which one's the stronger acid by looking at the conjugate base. If the conjugate base is more stable, it came from a stronger acid. These are the conjugate bases of these things here, the alkane, alkene, and alkyne. When we determine the stability of these conjugate bases, we see that this is the most stable conjugate base because the negative charge here is on an sp carbon, which has the most amount of S character. And that means that it's closest to the nucleus, which has a lot of positive charge. That's why it's more stable, because the negative charge is stabilized by the nucleus, which is closer. So since this is the most stable conjugate base, it is unreactive. It doesn't want to react. It's happy as it is. That means it's a weak conjugate base. And if it's a weak conjugate base, that means that this is a strong acid. Right? This here, on the other hand, is an unstable conjugate base because it's further away from the nucleus. And if it's unstable, it's more reactive. It wants to react more. And that means this is a strong conjugate base because it's more reactive. And then if this is a strong conjugate base, that means that this is a weak acid. Okay. So that's the reasoning why this has the lowest pKa and this has the highest pKa. Okay, let's go on to boiling point and melting point. So we know that these are alkenes with two substituents. We can label them as cis or trans. So the left one is going to be cis because the two groups are on the same side of the double bond. The right one is going to be trans because they are on opposite sides. Now, if you see R groups on this alkene right there, that means that they are going to donate electrons inductively, like that. R groups are electron donating groups inductively, right? So think of these as net dipole moments donating electrons into the alkene, like that. Think of this as physics, where this is a vector, and that's another vector. Let's add those vectors together. Like, let's say we do that. Starting from this point, we add the other vector. That gives us this net dipole moment here, right? Because I'm bringing this vector here, and I'm adding it to that vector, which means that I'm going to start from where the arrow ends at, and I'm going to end at the where it's going to. Where when I add it up, that's the net vector, or the net dipole moment, right? If we look at the other one, right? What do you guys predict is going to happen for for this one when we add it up? Yeah. Yeah, no dipole moment, because once we start at the tip here and we add the other vector, it goes back down to where it started. So there's a zero net dipole moment, right? That means that the cis alkene is polar. The trans alkene is non-polar. So based on that, which one of these do you guys think is going to have more intermolecular forces, more IMS? Yeah, the cis. And if that has more intermolecular forces, would that have a higher or lower boiling point? The cis. Higher boiling point, that's right, because it requires more energy to break those forces and boil them. Right. Okay, so that's the boiling point factor, which is different than melting point, because melting point doesn't look at the net dipole moments, it looks at something else. For melting point, we see that, let's say we have a lot of these alkenes in a flask, they do not pack well together, right? They're going to be jagged and stuff like that. They're going to be separated more. Does not pack well together. But the trans alkene, they pack very well together. Packs well, right? So based on that, which one do you guys think is going to have the higher melting point to separate? The trans one, that's right. So the trans alkene will have a higher melting point than the cis alkene. But the trans alkene has a lower boiling point than the cis alkene because of different reasonings. The boiling point is due to the polarity and intermolecular forces. The melting point is due to the stacking ability of the molecules. Okay. So boiling point, melting point, they are different. Okay. Now let's go over the stability of alkenes. The more substituted the alkene is, the more stable it's going to be, because think of it as like the carbocation. The reasoning is because of hyperconjugation. There's more hyperconjugation in this alkene because think of it as like a support system. Like this alkene has a lot of friends around it. And the exact reasoning is because these R groups here, like I said earlier, they donate electrons inductively or to hyperconjugation. and they like think about it as stabilizing the charge. If the alkene is more stabilized by charges, then that's like the more stable one because of hyperconjugation. Whereas the unsubstituted alkene here has no R groups at all. That is that is the most unstable because there's the least amount of hyperconjugation there. Right? This is monosubstituted double bond because there's only one R group. These three alkenes here are di-substituted, where the cis double bond is the same stability as the geminal double bond. Geminal double bond is when the two R groups are on the same carbon of the alkene. Cis is when the two R groups are on different carbons of the alkene, but they're on the same side of where the double bond is. Geminal is when they are on the same carbon, but they have the same stability. Trans alkene is the more stable di-substituted double bond compared to cis and geminal. And do you guys know the reason why trans is more stable than cis or geminal? Yeah. Yeah, because of steric hindrance. These R groups here are very close to each other. That means that they are increasing the steric hindrance, making this less stable. Whereas the R groups here are away from each other, decreasing the steric hindrance, making it more stable. Now, the tri-substituted is more stable because it's more hyperconjugation. Tetra is the most because of the most amount of hyperconjugation. And like we said, trans is more stable than cis because of steric hindrance. Trans has less steric hindrance. It is more stable. Okay. Which one of these alkenes do you think is going to be more stable? The terminal alkene or the internal alkene? Internal, great. Because internal has two groups. So this is di-substituted, and terminal is only mono-substituted. There's only one group there. And this is due to hyperconjugation. Okay. Which one of these alkenes are more stable, the isolated one or the conjugated one? Yeah. Yeah, conjugated because these alkenes here can do conjugation or resonance, right? Like these double bonds are able to do resonance with each other. This cannot do resonance because there is an sp3 roadblock there blocking the resonance, right? So this is because of resonance or conjugation. Okay. Yeah.
So even though it's more stable, that means it's still higher energy.
More stable means lower energy. Less stable means higher energy.
So is it the opposite with like alkanes? Because I know for alkanes, the trans isomer is lower energy, or is
Yeah, the trans alkene is lower energy. That means it's more stable than the cis alkene. The cis alkene is higher energy than the trans because it is less stable.
oh, so someone who's applying okay.
Yeah, yeah.
Okay.
It's the same for every single system. Higher energy is always more unstable.
Okay.
Lower energy is always more stable. Yeah. Yeah, there's a lot of like relationships between things like energy, stability, and also for like acids and bases, like weak conjugate base means stable conjugate base, and that means stronger acid. Now let's try these three practice problems here. Oh, you just skip the ad, like if you go to ad, you scroll down, you skip ad. Yeah. Oh, yeah. Yeah. Okay. Go. Jesus. Just put your UC email and you put it back in. Okay. Add. There you go. Uh-huh. Yeah. Oh yeah, yeah. Oh, did you sign in? Yeah. Oh yeah, you did. Yeah. Uh-huh. Yeah. Did you have only in A last quarter?
Yes, I did.
Oh, I see. Who was there? Oh yeah, it was only.
I believe
Vince.
in
Yeah.
do I just
Yeah, and then it might show an ad. You just click skip ad.
okay.
Yeah.
There we go.
Uh-huh.
Okay, thank you.
Yes, the practice is posted on the outline.
And then
Yeah. There. Yeah. Let's go. Uh-huh.
Thank you.
Yeah, no problem. Let's look at the first practice problem. Which one of these did you guys say is the most stable alkene? Yeah. Yeah, and why the middle one? Yeah, that's right. There are 4 groups attached to it. Like, let's say this is the double bond, right? The 4 groups are here, 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 and here. Those 4 groups are making this double bond tetrasubstituted. It has the most amount of hyperconjugation. Okay. Which one of these are the second most stable? Yeah, the one on the right, because it is tri-substituted. Now, the next one, there is two that is number 3. Two of them that is number 3. Yeah, the second one and the fourth one, because these 2 are di-substituted. And like there are Z. As well. And we'll go over E and Z when we go over nomenclature. That means that this is the number 4 because this is only mono-substituted. That double bond only has 1 R group attached to it. The hydrogens do not count as an R group. So that's why this double bond here is only mono-substituted. Yeah.
Are these all possible resin structures of the same?
No. These are all different molecules. They're not resonant structures of each other. But if there were resin structures to each other, the most stable one would be the major resin structure. Okay, now that's going to go with this right here. Let's say this is a carbocation. We know that this carbocation here is not only primary, but it is on the allylic position of this double bond. This is primary allylic, which can do resonance. Yes, where we can move this double bond here and give us this resonance structure there. Right. Same thing here. We could do resonance, moving that double bond there, creating a positive charge here. This here cannot do resonance. That is just a primary carbocation with no conjugation system nearby, no resonance there. This one can do resonance, so let's draw that resonance structure out. Okay. Which one of these double bonds do you guys think is the most stable double bond? The second one? This one? Okay, so this second one here is a geminal alkene because the two R groups are on the same carbon, right? There is one disubstituted of one that is more stable than this geminal alkene. Yeah. The trans alkene, that's right. Because this alkene is also disubstituted, but it is trans. And trans alkene is more stable than geminal and cis alkene. Yeah. So this trans alkene here is the most stable. And then the geminal one is the second most stable because it's disubstituted. And then this is the third one because this is monosubstituted. And this is the least stable because that's a primary carbocation, which is really unstable. It does not exist. There you go. Yeah.
Sorry.
Mhm.
For the second one, I thought that one would be more stable because it's substituted.
Oh, yeah. So when we look at the double bond right here, that double bond has hydrogens and two R groups, 1, 2, disubstituted. Right. It looks tri-substituted because usually you see things like this that is tri-substituted,
Oh,
but this here is not R group. These are two hydrogens, right? So this is disubstituted and it's geminal, which is a kind of new thing this quarter. For 118B. This is try. 1, 2, 3. Try. Okay. Any other questions on this? Okay. Now, more practice on the alkene stability. Two of these will have the same stability. So for these types of problems here, like I like to the extremes and then just figure out the middle in between. Oh, that's a different one. And it might want to add this what I'm yeah, and it is okay. Yeah.
Yeah, I think I would have myself consider.
Yeah. And did you get this outline too for the today's notes? Oh yeah, make sure to put a comma after. Yeah, there you go. Okay. Next. Add. Okay. Okay. Which one of these is the most stable double bond? The third one, yes. 1, 2, 3. Because this third one here is tetra substituted. Which one of these is the least stable double bond? The one on the very right. Yes, because that is unsubstituted, no R groups at all. Okay. Now, which one is the second most stable one? Yes, the fifth one, which is tri-substituted. Okay. And what did you guys get for the third one? Sixth one. Uh-huh. Yeah. Yeah. This is di-substituted and it is trans. We have two more di-substituted things. And this next one here, there is two of them. Like number 4, there's two fourth ones, two fourth most stable ones. Yeah. The first one and the fourth one, right? Because this is a cis alkene, this is a geminal alkene. Cis and geminal alkenes have the same or similar stability, right? That makes this number 5, the mono-substituted one. Right? Yeah. Yeah. Geminal alkenes are when we have two R groups are on the same carbon. These are the two R groups on the same carbon, right? So there are 3 di-substituted alkenes you can have, cis, trans, and geminal. For cis, the 2 R groups are on different carbons of the alkene. For trans, they are also on different carbons of the alkene. But for geminal, they are on the same carbon of the alkene. The 2 R groups are the same carbon. And cis and geminal alkenes are the same stability. Okay, now let's go over alkene nomenclature, where a regular 3-carbon chain is a propane with no other functional group, no alkene, no bromine, chlorine, oxygen, alcohol, stuff like that. Where this 3-carbon thing chain here has an alkene. And how do we want to number this? Do we want to number this left to right or right to left? Right, or right to left. Yes, because that will give us our lowest number. And we just put propene. We don't have to put 1 dash propene because it's automatically assumed it's there. Only for this case though, because there's only one spot for the alkene to go for propene. Right. That means that this is ethene. And for this one though, like the 1, 2, 3, 4, we do have to put where the alkene is because the alkene could start from carbon 1 or it can start from carbon 2. Right? Where this is 4 carbons long, so we could say 1 butene to show that the alkene starts at carbon 1, or you could say but-1-ene. This is the way I prefer it to be because when you add more substituents like alcohols and other functional groups on it, it's easier to see what the alkene is this way. But in this case, this is easier because there's no other groups attached to it. But when you add more, this will be easier to see. For the next one, this could be 1, 2, 3, 4. This could be but-2-ene because it's 4 carbons long and the alkene starts at carbon 2. And do we have stereochemistry here that we could assign as well for the nomenclature? So don't think of R and S because that's not the only nomenclature that you guys can do for power sensors. There's something else that you can do nomenclature with as well. E or Z, that's right. And here's how to determine E and Z. You first make a dashed line through the double bond, right? And then focus on 1 carbon at a time of the alkene. Let's focus on this carbon right here. that carbon is attached to a hydrogen and a carbon. The one with the highest priority is going to be the one with the highest atomic number, just like how we did for R and S in 118A. So that's going to be carbon in this case, right? And so let's do the same on the other carbon now. On the other carbon, the highest priority group is this carbon, where we see the two highest priority groups on the alkene are on opposite sides of the dash line we made. If they are on the opposite side of the dash line we made, this is an E alkene. E. Okay. Now, let's do the same for this one. We know that these are the two highest priority groups. They are on the same side of the alkene. So this is a Z alkene. And the way I like to remember this is that Z alkenes have the two highest priority groups are on the same side. The same side. These two highest priority groups are on the same side. Yeah. Now, try this one for a few minutes. Yeah. What is this on time? Another tutor who might take over. Like for all order. Yes. Or a summer session. Just put in your UC Vegas email and UC Vegas email. Yeah. Are you tired? Not yet. Okay. That would be. No. Okay.
Oh, no, yeah, you're getting your sample.
Oh. See, if we're supposed to add, just click skip ad. You'll say, yeah.
Thank you.
Yeah, no problem. You see this? Thank you. Does anyone want to come up and try this problem? So first, how do you guys want to number this train? Left to right, yes. So that's gonna be 1, 2, 3, 4, 5, 6. This would not be 7 because we could have a longer chain if we go up. 7, 8. So our longest chain is 8 carbons long, and we have a substituent on carbon 6, which is the methyl group. So what would be our base name if it's 8 carbons long with an alkene? Octene on carbon 2, octene, yay. Oct-2-ene, to show that the alkene is at carbon 2, it starts at carbon 2. And we know we have a methyl group at carbon 6, so that's 6-methyl oct-2-ene. Or it could have been 6-methyl 2-octene as well. What else are we missing here? There's one thing that's missing. E or Z, that's right. And this is Z, yes, because if we make a dashed line through this double bond, we see that our two highest priority groups are on the same side, Z. Yes. And in this case, there's also like 2 more acceptable names because this alkene has exactly 2 substituents. And if it has exactly 2 substituents, you can do cis or trans if it's not geminal. But just stick with EZ so you consistent with it, and then you don't actually accidentally put a cis or trans if it's like 3 or 4. So just to be safe, just do EZ so you are like used to EZ. Yeah. Okay. Now, this one we went over already. Yeah. Okay. Okay. Now these ones determine if you don't have to name it, just determine if the alkene is E or Z. What did you guys get for the first one? E? Yes. That's because make that there. Focus on this one. Highest priority group there. This one. Bromine has a higher priority than carbon. So that's the highest priority group. Opposite side, E. How about the second one? Z. Yes, yes. Third one? Yeah, Z as well. Because wait. Yeah. Z. So even though this group here looks bigger than this group has a high priority because this carbon and that carbon has the same atomic number, then we have to look at what's attached to it. This carbon is attached to 1 carbon and 2 hydrogens. This carbon is attached to 2 carbons and 1 hydrogen. Since this carbon is attached to like more higher atomic number atoms, this is the high priority. Even though this looks bigger, this is high priority, where the 2 high priority groups are on the same side, Z. Okay. Yeah.
The side, the right substituent is a higher priority than the left one because the right one is branched.
Oh, this one right here?
Oh no, the second one.
Oh, the second one right here. Yeah. So when we look at this carbon right here, the thing we're comparing is the first atom directly attached to this carbon right here.
Oh.
The first atom is this bromine and that carbon. The bromine has atomic number 35, carbon 6. Mhm. Okay, so there are different scenarios where like if it's in a ring, if it's not part of the main chain, and if it's part of the main chain, but there's 1 carbon attached to it, and if there's an alcohol. So try this one for 1 to 2 minutes. So what's going to be our number one carbon? Here. Yes. Would it be this or this? Yes, the one on the left. And do we want to number it this way or this way? Yeah, the first way. 1, 2, 3, 4, 5, 6. We don't want to do it like this. 1, 2, 3, 4, 5, 6. Because the pink way will have the bromine on the sixth carbon. The red way will have the bromine on the third carbon. We want the substituents to have the lowest number possible. So the red way is the correct numbering system. Yeah. Yes, alkenes take precedence over halogens. Yes. But it does not take precedence over alcohol. Alcohol has higher priority than alkene. So we know that we have a 3-bromo cyclohexene. The 1 is optional for the alkene here because it's going to be automatically assumed that it's on carbon 1 of the cycle of the ring. In this case, this is the only time when Z is optional because if it's in a cyclohexane, the alkene will always have to be Z because we can't have an E alkene in a ring. Yeah, that would not make sense. The alkene on the cyclohexane will be Z. That's why the Z here is optional. But you could put Z too if you want. Z. Yeah. So there's like multiple different possible names for these things. Okay. So let's say our main chain does not have an alkene, but the alkene is a substituent. In this case, the main chain is this cyclohexane, and the substituent is this 2-carbon alkene right here. If it's a substituent, then it will end in eno, right? Where we have 2 carbons as a substituent, so that would be etheno cyclohexane. You could put 1 there as well. That's optional. 1 etheno cyclohexane, but it's going to be assumed that it's on carbon 1 if there's no 1 there. Okay. For this one, the main chain is still a cyclohexane, 6-carbon ring, but this time the substituent is 3 carbons long. So that would be prop. And in this case, we do have to put a number now because the alkene can start on carbon 1 or it can start on carbon 2. In this example, the alkene starts at carbon 2, so it'll be prop 2 eno cyclohexane. Or you could say 2-propeno cyclohexane. This is a 6-membered main chain as well, where we also have a 3-carbon substituent, and that starts on carbon 1. So this is prop 1 eno cyclohexane. So it does matter if it's like prop or butyl and so on, but it doesn't matter for S because there's only one spot where the alkene can go, so you don't have to put a number there for etheno. Or it could be 1 propeno cyclohexane. Any questions on this part? Yeah. Uh-huh. Oh, yeah.
If there was like promo on the first position, it's not like
Oh, if this bromo was right here, then you would say this is Z. The first position. This one right here. And there's no bromo here. Let's see. This carbon, that carbon. Yeah, you would have to say E in this case. Because the two highest priority groups are on opposite sides. Yeah. Yeah. Okay. And there's one thing missing for the last problem here. And what is that missing thing for the last one? It could be trans or E. The first two did not have to include E or Z because we can't do E or Z on this alkene that has two hydrogens on the same carbon and two hydrogens on the same carbon. There's no way to do E or Z there, right? But there is a way to do E or Z here, so we have to include it and assign it in the nomenclature. Yeah. Okay. Now, here's another case where if the alkene is a substituent, but one carbon of the alkene is part of the main chain. So let's say this is the main chain right here, the 1, 2, 3, 4, 5, 6, 7, 8 carbon main chain. And this is the substituent right there on carbon 4 that is one carbon long. And that alkene, one carbon of it is part of the main chain. So that is going to be methylidine octane. Well, on carbon 4. So 4-methylidine octane. 4-methylidine octane. The octane shows that our longest chain is 8 carbons long. We have a methylidine on carbon 4. The ylidine shows that this alkene substituent has one of its carbons attached to the main chain. That's when we use ylidine compared to enol. We use enol when the alkene is not part of the main chain at all, but it's separate from the main chain. Right. Okay. For this example here, our main chain is this cyclopentane, and we have a 1, 2, 3 carbon substituent, where that is going to be propylidine cyclopentane. Because our main chain is this cyclopentane right here. Our substituent is 3 carbons long, where the alkene, one carbon of the alkene, or half of it, is attached to the main chain. If half of it, or only one carbon, is attached to the main chain, we use ylidine. And it's propylidine because the substituent is 3 carbons long. This was methylidine because the substituent was 1 carbon long. Any questions on this part? The common name for methyl is like, I think methylene, but just stick with the IUPAC nomenclature, just to be safe. Okay, so let's move on to when we have an alcohol that is higher priority than the alkene. If alcohol is higher priority than alkene, then we want our lowest number to be near the alcohol instead. So that's why we're going to number this 1 and not this carbon as 1, because alcohol has a higher priority than alkene. So we want the lowest number to be near alcohol, not alkene. Since it's 3 carbons long, we are going to have prop 2 ene 1 ol. Right. Or it could have been 2 propene 1 ol. This one right here is not optional. This is mandatory for linear branches on the alcohol, right? But the 1 will be optional if it's in a ring. Since this is not a ring, we have to put the 1 here. Yeah. We include the E if there's like 2 alkenes, like diene, or 3 alkenes like triene and stuff like that. in this case, we only have one alkene with an alcohol, so we could take out the E because if we put an E there, that's gonna be two vowels next to each other, like E and O, so that we drop that vowel. And for this case, this is 1, 2, 3, 4, 5. Where what do you guys think is gonna be the name of this substituent on carbon 2 here? First, how many carbons is it? How many carbons long? Two carbons long, right? And we know there's an alkene, right? Is the alkene part of the main chain or is it separate from the main chain? Separate, right? If it's separate, do we want to use eno or ylidine? Eno, that's right. So it's gonna be 2-ethynyl cyclopentanol. Right. Uh-huh. Yeah, 2-ethynyl cyclopentanol. Let's say we have something like this though. Let's say we have okay, what would be the name of this here?
Or propylene, cyclopentanol, cyclopentanol.
Yeah. It would be that's right. 4-propylidine cyclohexanol. Because at carbon 4 of the main chain, we have a substituent here that's 3 carbons long, which is why we have prop. And that substituent has an alkene, but half of the alkene is included in the main chain, which is why we use ylidine. And this is cyclohexanol, where we don't have to put the one here, it's optional because it's in a ring. If this wasn't a ring, then you would have to put the one there. Okay. Now, try these 5 practice nomenclature problems. 2 of them you have to predict the name for, and 3 of them you have to draw it out based on the name given here. Yeah. Mass spectrometry.
Yeah, or fragmentation.
Fragmentation.
Covered that,
Yeah, I think I'm gonna go with IR, HNMR, and J values first, and then fragmentation. So if we have time, hopefully I can, but we'll see, we'll see. Yeah, that was planned for today, but I realized that that's too much. Uh-huh. And when I took 1 B, like mass spectrometry was not taught for math class, so I had to like learn it. Like, but then I'm still confused on it. Like, I'll just like try to talk through it. can I have 5 volunteers to come up and try these problems? It's okay, you guys get it wrong. Like some people might make the same mistake. Yeah. Uh-huh. Oh, question? Oh, yeah. Uh-huh. Yeah. Thank you. See, here we go. Oh, you could write it on my iPad here.
Okay.
Uh-huh. Yes, you could use her
Okay.
iPad. Yeah.
I made it too big.
You can write it underneath as well. Uh-huh. Nice. Yes. So this is Z35 dimethyl octreene, where this is the numbering system 1, 2, 3, 4, 5, 6, 7, 8, longest chain 8 carbons. The 2 methyl groups are on carbons 3 and 5. That's right. Okay. Next slide.
Can I like number and
Yeah.
stuff?
Uh-huh.
Brian, I have a question on the first one.
Yeah.
So would you go for the longest chain in that case, or would you actually go for the, that one methyl there? Change that one to 1, 2, 3.
This one?
Yeah, so you get the alkene with the lowest number.
So the longest chain would always take priority over that lowest number thing. So you would always go for the longest chain.
Okay.
Yeah. Yeah.
The same question, but for the alkene.
Oh, like this or this here? It doesn't matter which is your number one. It could be this or this, you get the same answer.
Like where you started, the alcohol is what?
Oh.
Like, does longest chain take priority over the alcohol?
Yes, longest chain takes priority over the alcohol, and when we do the longest chain, we only talk about carbons. The oxygen will not count as number one. Yeah.
There's one I got, it's like C.
E. So imagine an invisible line through this double bond. Let's focus on this carbon here. This carbon has hydrogen and a carbon. This is the highest priority group for that carbon right there. For this one, which one has a higher priority? This methyl or this ethyl? Ethyl, that's right. So for that line right there, this is the highest priority group, and that's the highest priority group. They are on the same side.
Is there like a case where the longest chain would not take priority? Or is it always higher with the longest chain?
So it depends on which professor you have. The theory will always do the longest chain if it's a ring octane, right? Like let's say you have a really long octane chain and a cyclopentane. That octane will take priority over the cyclopentane. But for Levens, she will say that the ring will take priority over the octane. So depends on the professor. Pascal, I think he goes for the good, so the text, I don't know, nomenclature rules change every like 2 years or something like that. So I don't know. Yeah. It's just scary to ask him too. Like just give me like, no. Yeah. So this is E2-methyl hept 5-ene 2-O. That's correct. Where carbon 2 methyl group, alkene starts at carbon 5. And at carbon 2 there's an alcohol. Yes. And this is E because the 2 highest priority groups are on the opposite side of the line here. Yes. Okay. Has anyone done these 3? Yeah. Uh-huh. There you go.
This one?
Yeah. Yeah.
So trouble kind of like to quickly determine between E and Z.
Oh, easy. So the very first thing you do is imagine an invisible line through the double bond. Like just make an invisible line through the double bond in your mind, and then focus on one carbon at a time. From that one carbon, look at the direct atom attached to it. Like ignore everything else. Like look at the very first carbon attached to that carbon. And then you look at the periodic table, or like when you know like which atom has higher atomic number, that has higher priority. But if the atom is the same, right, then what you do is look at the atoms attached to that. And then if the atoms attached to that has a higher atomic number, then that has the higher priority group. Right. Yeah, does that make sense? Like how like for example, yes, this is correct for ethylidene cyclohexanol. Oh, like were you confused about this question or this question here? E, okay. So the first thing you do, make a line through that double bond right there, right? Then you look at one carbon only. Let's look at this carbon here first. What atoms are attached to that carbon right there, besides the other alkene carbon? Hydrogen and yes. And which so don't look at the other three hydrogens, just look at the carbon, the very first atom. Which has a higher atomic number, carbon or hydrogen? Carbon, right? So that's the highest atomic number. Let's look at the other carbon now. It also has a hydrogen and a carbon. And we said carbon has a higher atomic number, so that's the other highest priority group. If we see the two highest priority groups are on the opposite side of that line, that is E.
Oh, okay.
Yeah, and then if it's on the same side, like let's say this was switched, then that would be Z.
Okay.
So just always think of a line through that double bond right there.
So for the top one, how come it?
The double bond, the line here is going to be here now. The line is different every time, depending on where the alkene is.
But isn't?
1, 2. Yeah. Okay. This is good. This is for ethylidene cyclohexanol, where our main chain is cyclohexanol, 6 carbon chain with an alcohol on carbon 1, and on carbon 4, 1, 2, 3, 4, we have an ethylidene, which is 2 carbon, where one of the carbon is attached to the main chain. So that is why it's ethylidene there. Okay. Yeah, no problem. Okay, so for this one here, our main chain is cyclopentanol. So let's just do that first. And carbon 3, we have a complex substituent here, prop-2-enol. Since we have propes, that means that we have 3 carbons in the substituent. So let's say this is 1, 2, 3, 4, 5. 1, 2, 3. That's the probe. Where at carbon 2 of that probe, we have a double bond right there. Did you guys get this? Or is this part? Okay, let's get it. Now this one. Yeah. 3, 4, 5, 6, 7, 8. Did you guys get this for this part? Yeah, okay, let's get it. Okay. Yeah.
Is there gonna be a case where there's, a double bond in the ring? With the ending change from like cyclopentanol to cyclopentanol?
Yeah, it would change. Like let's say we have this. Alcohol has the highest atomic number. So that's gonna be number 1 right there. And now this could be 2 or this could be 2. We want to do the one that has the lowest substituent, which is this right side over here, because the alkene is on carbon 2 and there's nothing on carbon 2 here. Right. So that's 1, 2, 3, 4, 5. So this is 4 ethyl cyclo.
How much are you willing to spend?
2 ene. And since this is a ring, the number 1 is optional. But I'm just gonna put it, but it just yeah, but it's optional. That's acceptable as well. Yeah. Okay. Next one.
Who said?
Now, yeah. Yeah, yeah, and there'll be so let's go over spectroscopy, R, HNMR, and the new thing, J values. This chart here tells you like the important peaks on the IR. 1500 below, that's the fingerprint region. Ignore that. At 1600, the sharp peak there is now keen. Pascal doesn't like allow note card on his exam, so this is just a memorization thing where you have to like now memorize it. It's not like last quarter where like you have a note card of this and you just like look at it, but now you have to like actually know where it is and like what it represents. Yeah. 1700 carbonyl, 2100 to 2300 triple
What's
bond
this water
region,
in it though now?
alkyne and nitrile. At the 3000, yeah. There's always this sp3 carbon hydrogen regular peak right there. If you look to the right of it, if you see a sharp peak at 2700, that's the aldehyde. If you look a little bit to the left of it, a sharp peak at 3100 is the sp2 carbon hydrogen. If you see at the 3300, the sharp peak there is an alkyne SpCH. And at the 3300, this is like where the big peaks are. Broad peak there, alcohol. But you see a big broad peak that merges with the sp3 carbon
Has
hydrogen.
Joanna
with
carried
aspartic acid.
writer at all?
This could be alcohol or NH, secondary amine. We can't tell.
Huh?
Unless we have the chemical formula. If there's no
But why is the
nitrogen,
music so fucking loud?
if we see two fangs here, it could be a big, like two fangs. That's a primary amine, NH2 on the IR. Okay. Yeah, like these are important peaks, you know. Right. Some theory stuff. I think like this is gonna be tested on like multiple choice. Stronger bonds absorb at higher wave numbers. Like we see here, these are like the strong bonds, like hydrogen bonds, NH2, OH, carboxylic acids. All those strong bonds are higher in the IR. Bonds to small atoms like hydrogens absorb at very large wavelengths as well. Hydrogen bond, hydrogen bond, hydrogen bond, very big wave number. IR summary. Yeah. It's all theoretical stuff where IR uses infrared light to excite molecules. Yeah. Yeah. This thing here. Well, yeah, you just ignore this. This is Helix's 118B last quarter. I don't know if Pascal wants you to know that, but just know this for sure. If you know this, then you'll be good for IR. Yeah, it's good. Okay. Now this is Pascal's thing where he wants you to know the relationship between let's say this is wavelength. This is frequency. This E is energy. And this thing is wave number, which is the x-axis of the IR, which is the inverse of wavelength, and its units are centimeter inverse, or yeah, inverse of centimeters. So this is like physics again. If you have a, let's say, long wavelength, so like this, right? Well, I think a wavelength is from peak to peak, right? That's a wavelength. And let's compare that to this. So this here, the top one has a higher wavelength, and the bottom one has a lower wavelength. The higher wavelength will have a lower frequency. The lower wavelength will have a higher frequency. So think of frequency as like how frequent, like it goes from peak to peak. Since this is very small wavelength, it goes from peak to peak a lot of times. Okay, so they have an inverse relationship with each other. If wavelength is low, frequency is high. And frequency and energy, they have a direct correlation to each other. If frequency is low, energy is low. If frequency is high, energy is high. Okay, so this is very energetic because it has a high frequency. This is low energy because it has low frequency and a large wavelength. Right. And that also goes with the wave number as well for the IR. Right. Where we see that in the IR here, the highest wave number has the things with the highest energy or the highest frequency or the lowest wave number. So that might be a conceptual question on the multiple choice or explanation questions. I don't know how Pascal exams are, so I don't know what he's gonna test on this stuff. Yeah. Let's say, yeah, that's the relationship. And also, I know Pascal taught 118A like 2 or 3 quarters ago, and he included math in there with an equation on stereochemistry with the optical activity, the exploratory, laboratory stuff. So if he gives you an equation in lecture, he might test that equation on the exam as well. So just memorize that just in case. And he'll give you the numbers and you just have to do math on the exam. Yeah. But yeah. Let's see. Transmit intensity, incident intensity. Yeah. Okay. Okay. So here's the HNMR graph and its common things. The things at around like 12 and up is the carboxylic acid. Around 9 to 10 is the aldehyde. 6 to 9 is the benzene, aromatic hydrogen. 4 to 6 is the alkene. 3 to 4 is the ones where the hydrogens are next to an electronegative atom like oxygen, nitrogen, or some electronegative atom. 2 to 3 is the carbon that is next to a pi bond. So next to a double bond, next to a triple bond, next to a carbonyl. That's the alpha region. This is the regular alkane region, 0 to 2, right there. Right? And if you have an alcohol or amine, it's gonna be shown as a broad peak, not like the subpeaks with neighbors because of hydrogen bonding. So if you have an alcohol or amine, it's usually between 1 and 5 with the broad peak. So this is another memorization thing, where the more practice you do, the more like it will stick, hopefully. Yeah. Okay. Well, this ortho meta para stuff was for like the lab homework, but do you guys want to just skip this and go on to the next thing, or you guys want to go over like the lab homework as well? Yeah, go over it. Okay. So this ortho meta para stuff will not be on midterm 1. This is going to be on midterm 2. Because it's in the benzene chapter, where let's say we have a benzene ring, right? And we have 2 substituents on it. And those 2 substituents could be ortho, meta, or para to each other. This ortho meta para definition is a relationship term. Like, let's say we have 2 R groups, one R group here and another R group right here. If they are right next to each other, then that is ortho. Right? For meta, we have the 2 R groups separated by 1 carbon. And a way you can think about it is that meta M, this kind of looks like an M for meta. Para is when the 2 R groups are parallel to each other or across from each other. Right? This is para, parallel from each other. So since we used up 2 spots of the benzene ring, there are 4 other spots left for the hydrogens. And these 4 benzene hydrogens here will always show up between 6 to 9 on the HNMR because that's the benzene aromatic region. Okay. Let's say these are 2 different R groups in the ortho benzene. All of these hydrogens are different. There's no plane of symmetry, so there's no identical hydrogens. All these 4 benzene hydrogens are unique. So let's say this is a red carbon, this is a blue, this is purple, showing that these are different peaks. What should the red carbon show up as on the HNMR, depending on its neighbors? Like how many subpeaks should it show? Yeah, 2, because it has 1 neighbor. So it should be a doublet like that. How about the blue one? Yeah, 3, because it has 2 neighbors. 2 plus 1 is 3, triplet. Same as for the purple one. The pink one should have 2 because it has 1 neighbor. right? So you'll see numbers on it as well, where these numbers represent how many hydrogens are there on the benzene ring. Okay. So if you see this pattern here between 6 to 9 on the HNMR, 2 doublets and 2 triplets with like a total of 4 hydrogens, you know your benzene ring is ortho. That's how you tell. Now for meta, all these hydrogens are also unique. There is no plane symmetry, so they are not going to be equal to each other. How many subpeaks should the red hydrogen have here? Yeah, 1, because there's 0 neighbors, and that's the distinguishing feature for meta. If you see a singlet on the 6 to 9 range, then it's most likely a meta benzene. Blue is doublet, purple is triplet, pink is doublet. So the big sign here is that singlet. If you see singlet, most likely meta. Para is the one that's easiest to recognize because there is a plane symmetry where these 2 hydrogens are the same chemical environment and these 2 hydrogens are the same chemical environment. How many neighbors does this red hydrogen have right here? Yeah, 1. So that should show up as a doublet because n plus 1, 1 plus 1, 2. Same as for the blue one. But this time there's 2 hydrogens for that peak and 2 hydrogens for this peak. If you see 2 doublets between 6 and 9, this is a para benzene ring. So that's how you tell if your benzene is ortho meta para from the HNMR in the 6 to 9 range. Okay. Okay. So shoot, let's die. Let's see. Okay. So let's say there's no 2 substituents and we only have 1 substituent. We can have ortho meta para, but we will have 5 hydrogens in between the 6 to 9 range, where these 2 hydrogens here have the same chemical environment because there's a plane of symmetry down this middle right here. These 2 hydrogens have the same chemical environment, and this 1 hydrogen here is alone because there are no other hydrogens attached to that. There are no other hydrogens that have the same chemical environment as that hydrogen. Okay. Red would be what would red show up as on the 6 to 9 range here? Yeah, depending on what the R group is, it could be more downfield because if it's like a oxygen or something like that, it would be more downfield. But how many subpeaks should red have? So let's look at one of the red carbons here. How many neighbors does this one red hydrogen have? 1, that's right. 1 neighbor, which is this one. So that means that it should show up as a doublet, 2 subpeaks. Right. So it could be more detuned because of this R group, but the important thing here is that this is going to be a doublet. How about the blue one? What would the blue one show up as? Yeah, triplet, because this blue hydrogen here has 2 neighbors. 2 plus 1, 3, triplet. Pink one, triplet as well, because 2 neighbors here. Where the red peak has 2, blue peak has 2, the pink has 1. So if you see 5 hydrogens, 2, 4, 5, like 2 plus 2 plus 1 is 5, 5 hydrogens in the 6 to 9 range, then you know that there's only 1 group on the benzene ring. Okay. In the other case, with the ortho meta para, the total benzene hydrogens was 4. But in this case, this adds up to 5 because we only have 1 group there. So this is not ortho meta para, it's just 1 group on the benzene ring. Okay, yeah, no problem. So now let's do these one by one. The first thing we have to do is do DOU, which the equation is 2c plus 2 minus h minus x plus n all over 2. Okay, put that here. And problem number 1, the DOU is 2 times 9 plus 2 minus 10 all over 2. That's 18 plus 2, 20, 20 minus 10, 5, 10, 0, 2, 5. Okay. And do you guys remember what DOU is? Like what it represents? Yeah, degrees of saturation, that's right. Where how many DOUs will be an alkene show? 1. How about alkyne? 2. How about any kind of ring? 1. Right. If you have at least 4 DOUs, you most likely have a benzene ring. Because this benzene ring has 3 double bonds, so that's 3 degrees of saturation and 1 ring. 3 plus 1, 4. Right. For us to double check that, we have to look at the 6 to 9 range on HNMR. We see peaks in the 6 to 9 range on HNMR, so that confirms our benzene thing. Right. Now let's look at the IR. Have you guys memorized the peaks yet? Oh no. Okay. I'll bring it down. Here, I'll copy it. Say. Okay. Yeah. Oh no. Let's see. Yeah, no problem. See ya. If you see a sharp peak at 3100, what does that tell us? What do we have at 3100? sp2ch, that's right. Where that sp2ch can be in the benzene ring, right? So let's cross that out because we know what that is. The around 3000 is the regular sp3ch. How about a sharp peak at 1700? What does sharp peak at 1700 tell us? Carbonyl, that's right. So that carbonyl there is going to account for the missing DOU we have. We already used up 4 DOU, but we have 1 more. And that 1 more DOU is the carbonyl that we have in the IR. And the 1600 sharp peak shows us our alkene. That's right. So then we know that we have a benzene ring, but what kind of benzene ring do we have? How many substituents are there, depending on the 6 to 9 range here? How many hydrogens are here? Yeah, and that means how many substituents on the one benzene ring, right? Because I mean 1 group. Because we want 5 benzene hydrogens. 1, 2, 3, 4, 5. Okay. And since I have 2 oxygens, I'm just gonna guess that this is an ester. That's just a guess. Where I know that we have a carbonyl from the IR and the oxygen right there, right? So let's cross out these peaks because those peaks are used up already. But now we have to worry about these 2 peaks right here. What do you notice about this peak here? Like, where is it located at? What region? Is it deshielded or shielded? Deshielded, right? And what does that mean if something is deshielded? Yeah, connected to the electronegative. Let's say that those 2 hydrogens there are connected to this oxygen right here. Like these 2 hydrogens right there are these 2 hydrogens because they are right next to that oxygen, which makes them deshielded. It's kind of hard to see here, but this has 3 subpeaks. I mean, 4 subpeaks, 4 subpeaks. If it has 4 subpeaks, how many neighbors should it have? 3 neighbors, right? And we can say that those 3 neighbors are these 3 hydrogens right there. Where these 3 hydrogens has 2 neighbors. And it has 2 neighbors, it should show as a triplet here. Where these 3 hydrogens are those 3 hydrogens right there. To confirm everything though, we can look at the chemical formula and see. We have 9 carbons here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. That checks out. we have 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. That checks out as well. 2 oxygens, 2 oxygens. 5 DOU, 1, 2, 3, 4, 5 DOU. We have a carbonyl, which is that's good, and benzene ring with 1 2 So this is the structure for the first one here. Yeah,
How did you know that was ester?
yeah, I knew it was an ester because of the carbonyl right here. And also, I just guessed that we had 2 oxygens, so I just put the oxygen right here. Because let's try drawing this right here. Like, let's say that was an ester. Let's try doing this instead. Something like this, right? That means that how many neighbors do these 2 hydrogens have right here? Yeah, and that means that we would need a singlet peak on HNMR. There's no singlet peak here. So you can keep trying things out and seeing what works or not. This is not it because there's no singlet here. The more practice you do, the more like accurate guesses you can make, right? So you can try this and see that it doesn't work out, and you just keep trying until you get to this tester and then see that everything else makes sense.
I have one more question.
Yeah.
What is the range for being deshielded? Because you said that that one peak with the 2 and the 4 and like the 4 and some peaks, that's considered deshielded. Is it just like above 4 ppm?
Above 3, like around 3 and up. Deshielded. Well, deshielded and shielded is a relative term. Like this is more deshielded than this.
Yeah.
This is more deshielded than this, but this is more shielded than this. Yeah, so it's just like how we explain like things relative to each other.
Okay,
Yeah.
so then, can we consider like anything above 4 is like attached to something?
Electronegative, yeah.
So above 3 or 4.
3 to 4, 3 to
Okay.
4, yeah. 2 to 3 is gonna be next to a pi bond, like a double bond or a triple bond. Yeah. Any other questions?
It's like, can you repeat that again?
Yeah.
The difference between 4 and 5 and triple.
Yeah, so if you see peaks between like 3 and up, right, then you can say that those hydrogens are next to an electronegative atom like oxygen or let's say a benzene ring. Like it doesn't have to be electronegative, it could be like aromatic as well. Which is a 6 to 9 range, which is the aromatic benzene. Below that, 2 to 3 is the alpha region, which is the carbon next to a pi bond, like a double bond or triple bond. 2 and below is the boring regular sp3CHs. Yeah. Let's move on to number 2. The DOU of this would be 2 times 9 plus 2 minus 11 plus 1, because we have 1 nitrogen, all over 2. 18 plus 2. This is also 5. So I'm gonna guess we have a benzene ring as well, because we have at least 4. And based on that benzene ring, we can check 6 to 9. We do have peaks in 6 to 9. And what does this pattern tell you? Like what kind of benzene ring do we have? Para, that's right, because we have 4 benzene hydrogens, that means we have 2 substituents, and these 2 doublets here tell us that we have a para benzene ring. So let's put para here and here. Okay. Cross the peaks out because we used that up already. The 3100 IR sharp peak is the sp2CH bond, which is like the benzene hydrogen, so cross that out. 3000 is the regular sp3CH. We have a carbonyl at 1700 and an alkene at 1600. Okay. So do you guys notice how like these 2 peaks is the same peak as the previous example? Like where we have a peak at 4, where it's 2 hydrogens with 3 neighbors. I'm gonna say that we have a carbonyl and 2 oxygen, so I'm gonna guess that we have an ester again, the same ester as we had last time, like this. Right, where these 2 hydrogens right here attached to the oxygen are these 2 hydrogens here with 3 neighbors. That's why it has 4 subpeaks. But these 3 hydrogens right here has 2 neighbors, which is a triplet right here. Does that make sense? Yeah. So now we used up this peak and this peak. Now we just have that peak here. And what atom are we missing in the chemical formula? Nitrogen, that's right. And it's kind of hard to tell here, but you notice how all these other peaks here are sharp, like there's like jagged, like it's like a sword. But you see how this is like a little bit broad, it's like a little bit more wider than the other ones. This is the broad peak. And what do we say are broad peaks on the HNMR? Always your NH, that's right. And since this is two hydrogens, this is going to be NH2. Because NH2 or OH are always broad in the HNMR, which is here. It's usually between like 3 to 5, but the reason why it's more D-shielded than usual is because this lone pair on nitrogen here is directly attached to the benzene ring, which can do resonance with the benzene ring. If it could do resonance all throughout, then that makes this hydrogen even more D-shielded. D-shielded, because the definition of D-shielded is that the electrons are being pulled away by an electron withdrawing group, like electronegative atom, or this big resonance thing that's pulling the hydrogen away. That makes it very D-shielded. So that's why it's very, very up here, because of the resonance that's going on here. Usually, like imagine there's no benzene ring there, and it was just alone. Then this NH2 here would be like around 3 to 5 only. But it's higher than that because it's attached to a really, really electron withdrawing group, which is the benzene ring there. Okay. So let's double check. We have every atom, 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. 11 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's good. 2 oxygens, 1 nitrogen. That's good. And we got para and every DOU and functional group that we have. Okay. Any questions on number 2? Okay. So number 3 is the hardest one. This one here is the hardest one. Okay. Let's do the DOU. 2 times 4 plus 2 minus 6 all over 2. That is 8 plus 2, 10, 10 minus 6, 4, 4 divided by 2, 2. Okay. We don't have a benzene ring because we don't have at least 4 DOU. And we also don't have any peaks 6 to 9. No peaks 6 to 9, no benzene hydrogen. What does this peak look like here? Like the peak between 4 to 5, 4 to 6. What's usually in between 4 to 6 in the HNMR? Alkene, right? But let's double check the IR. What shows up in the IR if we do have an alkene? Like what sharp peak? 1600 or 1650, right? That's right. Where we don't have 1600 sharp peak there. What other peak do we have if we have an alkene? There's one more sharp peak that we can see. sp2ch at 3100. We don't see the sp2 3100, and we don't see a sharp peak at 1600 as well. So this would not be an alkene, right? But we do have a carbonyl. That's right. So that's going to be one of the groups that we have there. Yeah. And if this is around 4, what does that tell us? Like what is it next to? Yeah, it could be next to oxygen, right? And I'm gonna guess it's an ester because we have 2 oxygens and a carbonyl right there. So I'm just gonna put that oxygen right there. Where let's say that these 2 hydrogens right here, right next to that oxygen, are these 2 hydrogens right here, which is why it's D-shielded. How many neighbors would those 2 hydrogens need to fulfill this? 3 suffix. So yeah, 2 neighbors. That's right. So let's draw those 2 neighbors right there. Okay. Let's see how many carbons we used up already. 1, 2, 3, and we don't know what this is yet. We need 1 more carbon, right? And we already used up 1 DOU. We need 1 more DOU. And what are the ways where we could add a DOU? Yeah, a ring. We can add another double bond because that would add an extra carbon. We can add a triple bond because I'll add another carbon. But we can connect this and make a ring. And that won't add another carbon. That would give us 4 carbons. 1, 2, 3, 4. And 1, 2, 3, 4, 5, 6 hydrogens and 2 oxygens. Yeah. So a big sign to look out for rings is that if you have a little bit amount of carbons and hydrogens, and like a little bit of things on the NMR, then you most likely have a ring somewhere under each NMR. And that's, in my opinion, the hardest problem for the set. So number 4, DOU, 2 times 8 plus 2 minus 8 all over 2. It's going to be the same thing, I think. 16 plus 2. Oh, no, it's different. 18. 5. So I'm going to have a benzene ring because I have at least 4 DOU, and I do see peaks between 6 to 9, which is a para. That's right, because we have 2 doublets. So let's put para here and here. Do you guys remember what functional group is on 10 on the HNMR? Aldehyde, yes. And if we have, yeah, this is a typo, like the IR. If it's an aldehyde, what peak should be here on the IR? 2700, 2700, a little bit lower than 3000. So this thing is missing at around 2700, 2800 peak on the IR. Right? But we do have an aldehyde because of the HNMR 10. But that means that we have a carbonyl as well, which is that carbonyl right there. Okay. And now, what do you notice about this peak right here? It's a singlet, that means it has 0 neighbors, and it's de-shielded. Right? And we already used up 1 oxygen, which is that 1 oxygen right there. We have 1 more oxygen that we could just like put right there. And then put a methyl group right there. Where these 3 hydrogens right here is very de-shielded because those 3 hydrogens are right next to the oxygen, which are these very de-shielded 3 hydrogens with 0 neighbors, which is why it's a singlet. Yeah.
So like in the previous example, you said if you have 2 oxygens, it's an ester.
Yeah.
And was it because you only have like 1 substituent on your, you only have 1 substituent to add? In comparison to this, where it's like you have 2, so you can have like an aldehyde in one place and not either on the other.
In the other case as well, right? Like let's look at this one right here. Like this could have been an amide. And this could have been that group right there, right? To tell the difference is to look at this peak right here. This peak is very de-shielded, right? Which means that when we do resonance here of this nitrogen, you can only do resonance at 1 spot. So that, right? From here, we can't do any more resonance. It looks like we can move this double bond down here and like resonate, do resonance with the benzene ring, right? But we can't do that because when we do that, nitrogen will have a +2 charge. That's really unstable. So you know how this structure here can only do resonance like 1 time, but this one here can do resonance a lot of times. And what does that make it? Does it make it more de-shielded or shielded if it can move more? Like more de-shielded, right? Which is why it's more de-shielded than usual here. But that's more very like, yeah, that's, yeah. That's why it's this one and not the same idea here. Yeah, yeah. That is de-shielded, and this is not as de-shielded. That would be lower. Like if this was the molecule, then this peak cannot be that high. It has to be lower. Last one. 2 times 8 plus 2 minus 8 all over 2. That is going to be 5 as well. Wait, is it? Yeah. Okay. Benzene. And we could double check that. 6 to 9 here. So it's kind of hard to see, but there should be a singlet there. If there's a singlet here, what would that make this benzene ring? Ortho, meta, or para? Meta. Great. Because if we look back at the ortho meta para stuff, right here, meta is the only one that has a singlet. And the reason why it only has a singlet is because of this hydrogen right here. This hydrogen has 0 neighbors, which is a singlet. Ortho, all of these hydrogens has at least 1 neighbor. So that's why there's no singlet here. Yeah. So for number 5, on the exam, you'll get clearer HNMR peaks here. This was just like very tiny and small and hard to read because they reuse these questions every quarter for like 1 and B. But that should be a singlet right there, which is going to be meta.
Isn't there a singlet at the very left? Or is that something?
On the very, oh, this one right here?
Yeah.
Yeah. That is also singlet as well, but that exceeds the 6 to 9 range. So that's no longer aromatic, but if it's 12 plus, what function group would this be if it's 12 plus? What's the highest? Yeah, carboxylic acid. The highest, most deshielded thing on HNMR is the carboxylic acid, which is around 12 plus. Okay, so let's just put that carboxylic acid on one of the groups here. That means that we also have a carbonyl, which that checks out with the IR, because we have a short peak at, what is this? There. That's the carbonyl. Like there's no number here, but that should be the carbonyl, and that should be the alkenes, and this is the fingerprint region. Okay. You get clearer IR and HNMR on the example fully. Give me some sense. Okay. And what does that make this here? This is very similar to one of the problems we did previously. 3 hydrogens with a singlet peak and it's deshielded. Ether, yes, ether. Because it is deshielded and it has 0 neighbors. Where those 3 hydrogens there has 0 neighbors, that's the oxygen right there. And it's meta because that's supposed to be singlet. There's one of the peaks there. Okay. But you won't get tested on this NMR stuff for the first midterm. This is a second midterm NMR stuff. When you learn about the benzene chapter. Yeah.
What is in
Alkene reactions. And right now he's kind of like a week behind than usual than other 118B professors. So he probably won't finish alkynes. And the pace he's going right now is kind of like slow. So I don't know. I think, yeah. The reactions of alkenes, some of it, yeah. But he can assess you on like what he didn't teach in lecture, hopefully. Yeah. Tomorrow we're gonna finish up J values, what they mean, like the coupling constants and stuff like that, and do one practice problem on that, and then do the fragmentation with mass spec. Yeah. And then after that, 118A review on how to make alkenes, E2, E1, dehydration of alcohols. Yeah, that's it.